seeing is just not vision. It's like there are many more ways you can actually perceive the world. We have the computer and the network to make the decisions, think on what we see, and then we, based on what we think, we actually do perform some tasks. So as I said, like there are now multiple robots coming into the picture that now have to coordinate with each other. We have real and virtual worlds. So real world is what we all live in. Virtual worlds could be simulation. It could be an augmented or mixed reality kind of a setting wherein the robot moves in the real world, but it's actually being perceiving the data that's now in the simulated setting. And of course, there is always a human user in the loop. So if you consider a machine shop floor, you have human workers going here and there along with the robots. So the robots should not harm them in any way. And still do the tasks efficiently. You have the self-driving cars which now have passengers in them. They can have pedestrians walking around, other vehicles potentially. And on all of this, we should ensure the efficiency, but more importantly, the safety of all of these users. So as I was explaining, sensors and actuators are key aspects of any robotics or autonomous vehicle, because one of them helps you perceive what's around you in the real world, and the other helps you act on what you perceive. Now you have connectivity among the different robots or vehicles. You have connectivity among robots and the infrastructural elements, so that you need not perceive everything, because data gets used pretty quickly, right? So, for example, even in your single phone, which has 12 megapixels, cameras on that car are pretty more powerful, but even 12 megapixels is 12 million data points. And if you now have a 30 frames per second video running that you're now streaming, it gets pretty huge. The data gets pretty huge, and if you want to perceive all that information and act in real time, real time is basically this car going, nominal speed even 40 miles an hour, maybe 30 miles an hour. If you need even 1 second to make the decision of how you should take your next maneuver, it should be left turn or right turn or what exactly it should be, it can be pretty dangerous if it's 1 second or 2 seconds, because in that much amount of time, in 30 or 40 miles an hour, the car is going to move pretty much idle time. And now with these kind of things, the applications grow pretty fast. So as I was giving an example of self-driving car or mobile robot on a shop floor setting, if you now consider an ambulance that has to reach a patient as fast as possible, take him to the nearest hospital. Now we have to ensure safety, we have to ensure time optimality, and that's where all of these things come in picture. So for example, you have transportation involved, since you want to transport the patient from one place to another. You have healthcare involved. You have cities or the infrastructure involved, because you want to now plan a route that's not going to make you get stuck in traffic. You want to avoid even if the distance to the hospital is shorter on that route, you need to consider a route that will actually make you reach there faster, not just based on the distance, but based on other parameters as well. So all of this becomes pretty complex to solve. And when you have multiple things working together, I'm pretty sure you guys would have worked in groups, right? So what happens if you have a group of 4, let's say, 2 of the guys are doing good work, and the other 2 are not so much interested and they don't care as much. What happens to the group? I'm pretty sure you guys would have experienced something like that. So could one of you share your experience? How does that work? Does it end up being good? Not really, right? So now if you have multiple robots and 2 of them are just not as good enough, or if in a single robot you have, as I said, multiple screens working together. So you have multiple sensors, you have computers, you have actuators. Now they all should work together in order to achieve all of that. That's on the right side. So even if one of them decides, no, I don't want to work today, the end result is going to be that as well. So what is our research vision for connected autonomy? Well, research is a very big term. Don't take it that way. It's really not very complicated if you start getting the grasp of it. So what we earlier had was automated vehicle and a connected vehicle, and those were 2 different things. So automation was something that people from engineering backgrounds were particularly interested in. Connectivity is something that people from electronics backgrounds are mostly interested in. And then one day they decided that okay, we
could actually shake our hands, and make these two technologies combined into a single one. And that is when connected autonomy paradigm came into picture. What you have in connected autonomy is the benefits of both automation as well as connectivity. So, as we said earlier, think about a self-driving car coming at an intersection. Does it actually see everything around it? Or can it see everything around it? Even we as humans have to shake our head time to time to see if there are cars coming from other sides of the lanes. There might be a jaywalking person who is just coming at random time, like even if the light is red or something like that. And those kind of things the car may or may not be able to sense in real time. But what we can now do is take the help of connectivity, wherein one car can communicate with other, or it can even communicate with the infrastructure. So, for example, even before coming at the intersection, your car already knows what the light is at the next intersection. So it already starts slowing down if the light is red. Or if there is a jaywalking person and one car detected, it can now share that information with another car that, okay, I see a jaywalker, please be aware that he might come in your way as well. So these kind of applications now start fostering wherein you have the benefits of both connectivity and autonomy. And as he said earlier, these have this is the bigger picture, but at the small scale you have to make everything work in order to achieve that goal. So this starts with different components. What if, for example, in the car, the engine decides that I am not going to work today? Even if everything else is working, the car still won't move. Or if one camera suddenly shuts off. Even if other things are working, the teamwork of all the components in the car will not be fruitful or will not go towards the end goal of making this vehicle autonomously drive. Then we have the systems level. So, for example, if the one car is working, and as I said, the other car at the intersection, this car is relying on that it will provide me some data related to the state of the infrastructure. But the other car is like, okay, I don't want to share it with you. What will happen? This car might actually hit the jaywalker, right? So that is at the systems level. And at the systems level, you have now multiple systems which now have to work collaboratively. So as I said, in the take the intersection scenario again. So if one car is driving and the other car is coming and it's not deciding to obey the traffic rules, or it is not deciding to give way to the car we talked about earlier, they will both end up crashing, right? Or in a good scenario, maybe this car might be able to detect that that car is gone rogue and may be able to stop before it crashes. But there are a lot of things that can go wrong, and we have to take care it from the microscopic level to the mesoscopic level, as we like to call it. So with this, as I said, there are a lot of challenges, and the two key challenges are with respect to developing these systems and then verifying whether they are actually working good enough. So with development, as you can see here, I'm sorry that the picture is too small, but here there are a different, basically the field of robotics is an interdisciplinary one. You have to have knowledge from mechanical domain, you have to have knowledge from electronics, electrical. So for example, what will happen if you have a very good foundation in mechanical, so you build a great structure of the robot, and now you don't know anything about electronics, you just take a 12-volt battery and connect it to a small LED. The LED will blow up, right? Or what if, like, for example, you take a battery from this car and connect it to a small motor on a robot, maybe on the table there. That just won't work. Similar is with electronics. So if you, or even computer science, so you connect everything and you don't know how to code. You can't do anything with it really, right? So that is where you should have all this knowledge, and that is where teamwork actually comes into picture. So you need not need to know everything. You might know some parts of everything, but then you can have help from others, wherein now you collectively come up as a team and then build robots. And that's what I think you guys must be doing in the class. So not everyone will be doing everything on the robot. You will divide your task amongst each other and then you will work, and that's the smart way to do it. And that is with the development issue. Now coming to verification and validation, you have a lot of problems. So, a quick question. How many miles do you think you can, if you show that a self-driving car is driving, safely, it's not hitting anyone, then you can call it a good enough car, or you may trust to sit inside that in the rear seat without anyone sitting in the front. What would you say? What will it take for you to trust that vehicle just behind there?
I mean, the vehicle would have to go through like an extensive amount of like, because so if you even if you have multiple of those like that, you could, if you build them all the same way, you wouldn't have to test as much as you would with just the first one.
Yeah.
So you would just test a little bit from the first one. The first one you would test like an extensive amount just to make sure that it works. And then if you just duplicate it, you're not going to have to test as much.
Yes, but
So
now when you say extensive,
like probably for, I mean, the first one this is already built, but like probably like a year, like at least.
here is the time. So I'll just keep it in the lab. I'll sit around. I'll say here I've tested it around for a year. Will that work? No, right?
So what researchers currently are saying that they need at least hundreds of millions miles of driving the vehicle without it hitting or doing anything wrong to now trust the vehicle. And that, for example, that amount, the number, 100 million miles, just keeps on increasing because we are never there yet. So companies decide, okay, I want to test 100 million miles. They do it. And they think, and they know that their thing is still not trustworthy. So they next year, in a few years, they start saying that, okay, we need 200 million miles to trust the vehicle. Okay, we need 500. And there is just no end to it. So the thing is, you really need a lot to trust these things. So what do you think, in percentages, what's the chance that this vehicle will hit someone?
Probably like 1 in 4 or 1 in 4.
Yeah, this thing might hit, okay? We are still in the research phase. They're not actually trying to put it on road.
Yeah.
But even if one person, you think, that means this vehicle will be hitting a person, one person in each 100 is cheap. So if there are a lot of people, it will just like say, okay, one person is good enough. I'll just hit that person and go. Will it be good enough? No. 0.1%, that's 1 in 1,000 people. So every 1,000 people it sees, it runs over one of them. So even at that small percentage values, it's really critical that this system doesn't behave wrong. So that's the reason that it needs extensive testing and verification and validation. And down there, to just give you an idea of the complexity for development as well as testing,